Okay, so this is lecture 3. Welcome. And I'll do a brief review from the last lecture and then we'll get more into moisture. So, we started the discussion for atmospheric moisture. We learned that a phase interface, so where two things of different phases hit each other, there is a constant phase change of water molecules. And so it's the rate of change that determines the net increase or decrease of the amount of each substance. So if there's net evaporation, there's going to be more water vapor, while if there's net condensation, there's going to be more liquid water. So if they are equal, they're going to stay at the same amounts. And then we introduce the concept of cloud condensation nuclei, which is just a particle in the atmosphere that water condenses onto. And you have to have this condensation nuclei to get raindrop formation. So, yeah, we talked about the falling iguanas. It's very cold. What air mass might be responsible for this? Well, I'll tell you what air mass is responsible for this if they don't tell you. It was probably a cold polar air mass that moved down and hit Florida. Normally, they don't go that far south. Sometimes they do, though, and that's how you can get those tornadic storms in Florida and a lot of water spouts. They do. I lived in Mississippi for a while. I've lived in Alabama. They do get down there and they create some really nasty tornadic storms at the interface of those two air masses. All right, good. Now we can talk about cloud formation. Most clouds are made up of millions of tiny liquid and solid cloud droplets. So they're too small to see individually with the naked eye, but they're larger than CCN, the cloud droplets. So you have this nuclei, and then you have 10 times as many, like 10 times the mass with water vapor, or not, that's condensed onto it and turned into liquid water. 10,000 times larger than water molecules. So 10,000 times larger than Mickey Mouse are these droplets up in the clouds. So it's not water vapor. These are now droplets, and they form into clouds, and that's like the white stuff you can see. It's liquid water, and it is solid water. Concentration, 1 million cloud droplets per liter of cloudy air. 1 billion per cubic meter. So, yeah, that's a lot. By definition, the air inside these clouds must be at least saturated. So, evaporation and condensation, in order for the cloud to remain, evaporation and condensation must be the same. And for the cloud to grow bigger and form raindrops, the evaporation must be less than the number of condensation events. So the cloud droplet the condensation rate is greater, so you have more liquid forming than gas. Why at least saturated? To keep drops from evaporating and the cloud from disappearing, the rate of condensation must be greater than the rate of evaporation. By definition, saturation is when the rate of condensation is equal to the rate of evaporation. So, to maintain a cloud, the air must be either saturated or supersaturated. At least saturated. Yeah, so that's what I just talked about. I kind of predicted this slide. I'm getting really good at prediction. I guess that's like a part of the meteorology major. It's kind of cool, isn't it, to just like be able to forecast the future. It's amazing we can do anything at all, really. What is fog? So, the air near the surface is usually unsaturated. But, so typically, when you're standing outside, the rate of evaporation is greater than the rate of condensation. So you don't have clouds that form at the surface. Fog forms when the air near the surface becomes at least saturated. So it's just a cloud that forms near the ground. It's pretty simple. When we discuss the atmospheric conditions needed for cloud formation, we rarely discuss vapor pressure and saturation vapor pressure. We more commonly discuss relative humidity and dew point temperature. That's true, because you don't see the weather guy going on TV and being like, oh, the vapor pressure is 40, I don't know what units they use. Anyway, yeah, you don't hear them talking about that, though. So, review from, it says from week 1, but we're in the summer, and we gotta really get on it, so this is review from day 1. So, the vapor pressure over the saturation vapor pressure times 100%, that's the relative humidity, and it depends on the amount of moisture in the air and the temperature of the air. So, if the air is saturated, the vapor pressure and the saturation vapor pressure are equal, and so the relative humidity is 100%. Dew point is also another way to talk about which saturation occurs. So if it's subsaturated, the temperature is greater than the dew point, and the relative humidity is less than 100%. Saturated, the temperature and the dew point are the same. And supersaturated, the temperature is less than the dew. Yeah, the temperature is less than the dew point. It feels wrong, because for so many years they were like, the temperature is not less than the dew point temperature, but maybe a little bit. So the closer the temperature is to the dew point, the higher the relative humidity. Summary of more of that kind of stuff. So for water vapor to condense onto CCN, the air must first reach saturation. The condensation rate has to be equal to the evaporation rate. And then it has to go beyond that to get the condensation events to occur. So how do we get this cooling? To be discussed. Clouds and precipitation. Are we reviewing this slide again? Okay, I guess they put the same slide kind of twice. Okay, so, any cooling past T equals TD will cause some of the water vapor in the air to condense onto CCN as liquid cloud droplets. So how do we get this cooling? To answer this, we must revisit heat transfer mechanisms. Here they are. Bada bing. Very important. So radiation, we talked about this a couple times. So this is just like you have heat waves coming off the sun, and it like electromagnetic waves. So this is the sun radiating the earth. Another example of radiation, you put your food in the microwave and it's hit with these microwaves. And then another one is conduction. So this is when you have heat transfer from a warmer to a colder substance via direct contact. For example, putting your hand on the stove and you're like, wow, that's really hot. That's conduction. It's fast. Or like walking on a hot pavement outside. Convection, movement of warmer fluid into colder fluid. They love the steam rising from the coffee cup example. I love it. The quiz loves it. Keep that in mind. And yeah, it's also boiling water on the stove. You have the air bubbles moving up. And you have lava lamps. Those are really great. And the clouds outside, that's convection. We do a lot of convection in meteorology. Can you guys hear my cat meowing? Wait. I stopped talking, he stopped meowing. Yeah, he likes to come into my room and tear everything off my walls, so I have to like kick him out while I'm giving lecture, because yeah, he really likes to tear the stuff off my walls. He likes to eat thumbtacks. Yeah, we really had to switch to nails in this home because he's the thumbtack eater certified. Okay, parcel theory. Love parcel theory. Parcel theory is awesome. Parcel theory has its problems that makes your forecast wrong sometimes, but for the most part, parcel theory is amazing. And it basically says that at the surface, You have this blob of air that can expand and contract, and it doesn't mix with the air around it. So, like, that's not going to be true, right? Like, in real life, you're going to always have mixing at the edges of these things. But it's like a good way to think of things so we can do math on it and we can think of them as opposed to the air around them. So you have an air parcel, which has certain properties, and then you have the environment around it, and the air parcel will move based on its temperature versus the environment temperature, or its moisture and the environment moisture. Yeah, a lot like balloons. I would say so. Yes. Okay, so what happens when they rise? So when you go up in the atmosphere, you think about it like the gravity thing, there's less force pushing on something the further away you get from Earth. It's less dense. There's less air molecules. Like, most of them are centered towards the ground. So as you move this parcel up, since there's less pushing down on it, it's able to rise and expand. So as an air parcel moves up, it expands. And if it sinks, it will contract because more of these molecules are there to push down on it. So as this parcel expands, its molecules spread apart, and when they spread apart, they're not hitting each other as much. They cool down. So a parcel rises, it expands, and it cools off. So decreasing the pressure of something or expanding it and making it less dense is going to cool it off. But if you were to flip this around and you were to take this thing and you were to push it towards the ground, you think of like all of these little molecules inside of it are now being forced to like rub together and hit each other and stuff. The temperature is going to increase. You've got more pressure on the outside of it, and it contracts. So that's why warm air rises, because it is trying to reach an equilibrium. The air is too warm, so it literally rises to cool off. It's actually kind of a miracle. So let's talk about how clouds form. We have this cute sun. So the sun heats the ground via radiation, so it skips all this. Some stuff happens up here, but we don't really talk about it. And then we get this ground heating up. Great, so now we have a bunch of parcels forming. So yeah, the ground heats the air molecules in direct contact with the ground via conduction. So there's these things that start off at the ground, these air that's being influenced directly by this hot ground. And because it's closer to this hot ground, these parcels here are now warmer than the air up here because it's farther away, so that they're just not going to get heated up. Like we discussed earlier, the Earth is heated from the ground up. Okay, we skipped a couple steps because I scroll fast. Okay, so these warm, less dense air parcels, they're less dense because the stuff is moving faster inside of it, and they're expanding because they're warm. They want to rise, like warm air rises. So via convection, not conduction anymore, but convection, these parcels start rising upwards towards the colder air. They want to cool off to create an equilibrium, so they're going to rise. And as they rise into the lower pressure environment, they're able to expand because there's less pressure on them, and they are going to cool off. Well, the parcel's going to keep rising, and it's going to keep cooling. And if you're forming a cloud, the temperature is going to cool to the dew point. So the air is, quote unquote, holding. I had a professor say that we're not allowed to say that, but I'm just going to say it. So the air is holding as much water vapor as it can, but there's not a cloud yet once it hits the dew point. But once the air parcel rises past the point where the parcel temperature is equal to the dew point, the air can become super saturated. So the temperature inside of it is less than the dew point. So the parcel is very, very wet. Like, it is more than saturated. There is more condensation events going on than evaporation events, and so we start condensing onto these little CCN, and the cloud forms. Rising motion is necessary for cloud formation. Facts. True. That's why the desert, where the air is sinking from the last lecture, that's why you don't get much clouds or rain out there, because the air is sinking. You need this rising motion in order to get the clouds to form. This allows the air parcels to enter environments of lower pressure, which leads to cooling to the dew point temperature, and then cooling past the dew point temperature, which is supersaturation when clouds form. We only showed one air parcel here. Well, in the first slide, they showed a whole bunch, so you can just assume that this is happening all over. So you have to have a lot of little air parcels around doing this to support a cloud. This clouds result from nature's quest for thermal equilibrium. Now that's beautiful. Yeah, so it wants to cool off hot things and warm up cold things. So the ground is hot, and so it just wants to cool off the hot ground. So it will rise until it's in equilibrium. Yep. So in short, the sun heats the ground via radiation. The ground heats the parcels via conduction. Air parcels rise via convection. The air parcels expand and cool as they rise. The air parcels cool to and past the dew point temperature, and then the cloud forms. Wow, how heavy is a cloud? So a bunch of math. Let's see what they did here. So my cat is hitting the door stopper under my door again. It's really a talent. I don't know how he reaches his paw underneath the door and does that. He really wants to talk and tear things off the wall. So let's talk about this little formula really fast here. So the volume is 1 kilometer cubed. Wow, that's pretty big. Yeah, I guess that's a modest cloud size. So 1 cubic kilometer, which is 10 to the 9th meters cubed. Typical cloud liquid water content. So liquid water content is 5 times 10 to the negative 4 kilogram per meter cubed. That changes a lot, but I guess that's a good, reasonable value. That's my cat again. So mass is equal to volume times the liquid water content. So 10 to the 9th, they forgot their units, but 10 to the 9th meters cubed times 5 times 10 to the negative 4 kilogram per meters cubed. So the meters cubed cross off and you're left with kilograms. So 50,000 kilograms. I don't know what that is in pounds. Maybe like double that or something. I don't know. I don't know how to do that conversion in my head. But according to this slide, this is the equivalent to the weight of 100 adult elephants, which is, I'm assuming that's a lot. Yeah, clouds are heavy. How heavy is a cloud? We just did the calculation. So how is the weight of the cloud held up? This is a question that bothered me for years, and I had to think really hard about it, but it kind of makes sense. You have this constant rising motion of air parcels called an updraft, which keeps the droplets aloft. So this upwards motion holds it up. Like, you have this physical upwards motion that keeps the cloud in the air. But if the cloud keeps growing and the droplets get too heavy to be suspended by this updraft, it will fall as precipitation. Gravity will take over, and the force downwards will be greater than the force upwards. So precipitation is a general term that can include rain, snow, sleet, freezing rain, ice, grapple, and or hail. I think that covered... I'm trying to think if I know of any more precipitation other than this, but I think that pretty much covers most of it. A downdraft is a column of descending rainy air. So you get what you have an updraft, and then once it gets too heavy and it starts falling, you get a downdraft. And if you want the storm to stay alive, you hope that these two aren't touching or like overlapping. If you want a tornado, they should be touching but not overlapping. We'll get to that later in the semester. Average cloud droplet size, 0.02 millimeters. average raindrop size, 2 millimeters. Pretty impressive difference. Yeah, okay. That does it for this one, but I think we have one more PowerPoint for today. Yeah, we talked about this just now. So let's talk about rain formation. So it's different than just you have to get the cloud condensation nuclei first. You need to have a cloud droplet. So first order of business is that condensation events are more than the evaporation events. That's the starting process. After you have that, then it splits off in two different ways to form rain. That process alone that I just talked about is not enough to grow it to the size of a raindrop. You have to have a little extra oomph. So I will talk about two ways that this happens. The first one is the warm rain process. This is where the temperature of the cloud is entirely above freezing and it contains only liquid water. You're not going to find that here in Oklahoma. This happens like out in the middle of the ocean, near those equatorial air masses, the ITCZ, rainforest. That's the warm rain process. Pretty much all rain here in Oklahoma is cold cloud process. So it means that the rain is going to start out as snow, pretty much. So the temperature of the cloud is not entirely above freezing. It can be entirely below freezing, or have regions of both freezing and below freezing air. The cloud contains either entirely ice or both ice and liquid water. So for those big storms, a lot of times you find both ice and liquid water. You can, in the winter, you can have ice, and once it like gets close to the surface, the snowflake melts and turns into rainwater. Or if it doesn't melt, it will just fall as snow. So let's talk about the warm rain process a little bit. So the cloud droplets form and grow in a supersaturated environment. So this whole thing is supersaturated, but they grow more slowly as they get larger, and then they continue to grow by colliding with each other. So this is called the collision coalescence process. So the warm rain process is literally just cloud droplets running into each other and becoming big. It's pretty simple. And then once they get sufficiently large, they will fall out as precipitation or rain, because they're not going to fall out as anything else other than rain because it's above freezing. Cold rain process, a little different. So ice particles form and grow in a supersaturated environment. So this is different because we have ice particles above this Bergeron line. That's what this 0 degree line is called. Ice particles grow more slowly as they get larger. So similarly, ice particles continue to grow by colliding with each other. So this is called aggregation. So aggregation is when you have ice particles hit each other. So collision coalescence is for rain, and aggregation is for ice particles. And once they get sufficiently large enough, the ice particles fall into the warm air, so past this Bergeron line, and they melt into raindrops. So this is what we have in Oklahoma. We have these ice particles that hit each other, and then they form raindrops. Raindrops fall out as precipitation. But wait! We've been using this picture of a cloud all semester. That's true. That's true. Can you tell me what's wrong with it? Well, I can tell you what's wrong with it. There's no ice. Wait, okay, I was wrong. Okay. It's kind of funny. Okay, it's true. Okay, the bottom of clouds are usually flat. True. And raindrops don't look like this. I mean, they do closer to the surface, but in the cloud, like the cloud drops usually look like little Easter eggs. Raindrops, oh my gosh. Really? Who drew that diagram? Somebody took the time to make that. That's pretty impressive. Okay, raindrops are not teardrop shaped. When they're small, they're less than 1 millimeter, they're spherical. And when they're large, they're oblate spheroids, so that's the shape of the Earth, also known as hamburger shaped, I guess. That's kind of funny. Because of the frictional forces and air resistance on the bottom and the top. So yeah, no teardrops on my guitar here. Like, these are spheres. Okay. Precipitation types and formation pathways for cold clouds. The truth is, most precipitation starts as ice aloft. No shocker there, I've said it like 3 times. Okay, example, it's a hot April day in Oklahoma. It's 95 degrees Fahrenheit. Dang, that is hot for April. That is hot for April. At the surface, and some storms are starting to roll in. How shallow would the storms have to be entirely liquid? Assume the temperature decreases at a rate of 7 degrees Celsius per kilometer. So they're giving us a little leeway by making it 95. So, let's see what they did. So the cloud top temperature had to be above 0 degrees Celsius. 0 degrees is less than... It's 35, 7H... minus 7. Okay, I see what they did. I don't want you to have to worry about this. This is a summer class where we are trying to have fun. But long story short, the height is less than 5 kilometers. Do you think the storms are that shallow here in Oklahoma? No. There we go. Here's our big... If we wanted it to be a non-ice storm, if we wanted it to be a pure warm rainstorm, it would have to stop right here, like at the 5 kilometer line. And this is like where it starts being cold and rainy. And this is like, this penetrating top is hitting like the 15 kilometer line, and this 12 kilometer line is the top of the anvil. So, no, it starts as snow here. That's the important thing. Clouds form snow, which forms rain in Oklahoma. Yes. Oh, that's cute. Diagram. Okay, so we're talking about rain. So, rain. The temperature is above freezing at the surface. So this is the temperature. So this is 0 degrees temperature. This is less than 0 degrees. This is greater than. So you have this raindrop, and it's falling down, and it's less than 0, and they didn't put the height amount, but somewhere in the atmosphere, it gets above this 0 degrees line, and then it melts. So that's what normally happens when it rains here. I would say almost 100% of the time, that's what happens when it rains here. Okay, snow, similar, but it never hits above the 0 degree line. It just goes down, and it stays below 0 the whole time. Sleet, so this one's kind of interesting. So you have this droplet, and it's going down, and it's frozen most of the time. But somewhere you have like an inversion layer where it's warmer in the atmosphere. So it heats up, and it's above freezing for a little bit. But then it comes back down, and it has enough time to refreeze into these ice pellets. So it has a good amount of distance still to fall. So it's a snowflake that melted into a raindrop that refroze before hitting the surface, and it creates little pellets. Freezing rain, ultra dangerous. I moved here in 2020, and there were 3 freezing rainstorms, which I found just absolutely impressive and unlike anything I've ever seen. So this... You have, like, a good amount of time with this. So you have a good amount of time of it with, above 0 temperatures. So it's going down, it's snow, and then it gets somewhere in, like, the upper mid-atmosphere, and you have a big warm layer. So it spends a lot of time above freezing, and it turns into a raindrop, and it falls, and it's still a raindrop. But at the surface is freezing. So... the water is super cooled, and when it hits that surface, it just freezes on impact. Like, it cools down, and then it hits the surface, and it freezes as soon as it makes contact. Which is, it's very dangerous. It doesn't have time to, like, freeze back into the pellet shape, like it did on the last one. See, like, it had a lot of time to refreeze into a little pellet. This one, it doesn't have time to refreeze until it hits the ground. Great, so here's all of them next to each other. Yeah. My cat is so sad. What's this profile? If I was forecasting this, I would say, well, first of all, they didn't put a temperature line or any values for the atmospheric level. So that's a problem. But what is that profile? Maybe sleet to freezing rainish. I don't know, like mixture, grapple. Yeah, I don't know. Takeaway. Winter weather forecasting is hard. I agree with that. There's a lot to know. It's not that hard. You can learn it. Don't worry. It's not that hard. I didn't write these slides. I would never write winter weather forecasting is hard. Don't get down on yourself. You can do it. Stability. Okay. Sun, heats. Okay, we went over this several times. Okay. This is just the stuff. I'll let you, like, if you want to pause and fill out your notes, feel free. Okay, okay. The process of forming clouds seems nice and straightforward, and it's not. Yeah, so what factors will lead to clear days versus cloudy days? We have to talk about stability. So, stability, so a key term, an environment is the space surrounding the object of interest. Yes, so the object of interest, okay, I don't know what all this ball stuff is, but, okay, I would rather not even talk about this. I do not want to talk about this. Don't worry, this is not on your exam, but I'm just going to explain stability in a way that makes sense, and if you still want to fill out these... Okay, maybe I will talk about it. Let's just look at it. Think about it. Okay. Stable. Okay, the ball is inside the bowl. When the ball is pushed by some force, it will return to its original starting location after the force is removed. Okay, yeah. So in the atmosphere, this is analogous to an air parcel being lifted up by some force and then returning to its original starting elevation. So that's the important thing. If you don't get the ball in the bowl, that's fine. What's important about something that's stable is that when you remove that air mass, if you move it up or move it down, it's going to slingshot back to where it was. It liked where it was. And usually this is when the density or the buoyancy of the parcel is the same as the environment. So stability is equilibrium. It's good. It likes being stable. Okay, so unstable. The ball is on top of the bowl. Yeah, I guess it would be unstable on top of the bowl. So when the ball is pushed by some force, it will continue to move and accelerate after the force is removed. In the atmosphere, this is analogous to an air parcel being lifted up by some force and then continue to move and accelerate upwards. This scenario forms clouds. So yeah, an unstable air mass, if you get this thing moving, like you've started at the surface and it starts moving, it's just going to keep moving in the direction that you moved it. It doesn't like where it was originally at for some reason. So it's going to keep moving until it finds somewhere it likes to be. So that's unstable air. Doesn't like where it's going to be. It's just going to keep moving in the direction it's pushed. Okay. Yeah. So, yeah. Neutral stability. When the ball is pushed by some force, it will remain where it is after the force is removed. So, this is like an air parcel being lifted up by some force and then remaining where it is in elevation. So the difference between unstable and neutral is like this thing is just going to keep flying, like it's going to keep going, but this one it's like you push something and like eventually it's going to stop once the force stops, where in this unstable it's just going to keep going even if it's not being pushed on anymore. It's just like got that buoyant force now. So we have this ball, the initial starting position. A force is applied to the ball, causing it to move. And when the force stops pushing on the ball stops and there's no further movement. But this one, like, if this was unstable, like, you would push on the ball would keep going, and it would just keep going even when you stop pushing on it. So, yeah, it's not too difficult. And I think that actually ends our discussion for day 3. So if you have any questions, let me know. And don't forget your quiz that opens on Monday. Bye!